Hi, this is Keely, and we're going to derive the volume of a sphere using calculus today. So to start things off, we need to look at what's changing in our object. So we go from 0 to some r, that's our radius, and then just like when we did the area of a circle, we have to come around theta. And theta is going to go from 0 to 2 pi, but it also has a component that we have to get how far out it is to get the distance it goes around. And with that and changing r, we can get the area, but to get the volume, we have to do one more parameter. We have to go from the top of our sphere all the way down to the bottom. So it looks sort of like this. So we're going to get r, and then we're going to get phi, and then we're going to take that whole thing and rotate it around until we make that sphere. In order to do that, we need to look at our parameters. So, for example, r is going to go from 0 to our arbitrary r, and that's just dr. That's simple. It's just figuring out the length of that line. No trouble. Just that minus that, done. For theta, that goes from 0 to 2 pi, but to get that size, we have to account for r, how far we're out, and the changing theta as it goes all the way around. And to get the whole volume, we have to go from here to there, because this just gives us that disk. We want to rotate that whole thing around. So we need to do one more from 0 to pi, because we're going to go from here all the way down to there, but we need this side here. And so if we use sine, sine is opposite over hypotenuse. And so if we do that, that means this side is equal to r sine of phi. And so we're going to use that, r sine of phi, d phi, over here. And we've got to combine all three of these. So we're going to get a triple integral. Okay, so we need to take dr from 0 to r, dr. Then we're going to take phi from 0 to pi, and that's going to have r sine phi in there. And then our last integral is for theta, and it goes from 0 to 2 pi. It also has an r in d theta. So we took all these and kind of combined them right here, and we can simplify that because that's going to be r squared. So let me rewrite this in a nicer form. Still keeping my color code as best I can, unless I mess it up. R squared sine of phi d theta d phi dr. I'm going to usually start off with the inners and work your way out. So I'm going to start off with theta. And since these aren't variables that have to do with theta, we're just going to end up, integral of d theta is just theta. All right, so when we do this, we get 2 pi minus 0 Well, the minus 0 doesn't really matter, so we end up just with 2 pi. Let me fill in the rest so I don't lose track of things. All right, now that 2 pi can be pulled out because it's now a constant. Now we got to integrate phi. Well, if you take the integral of sine, you get negative cosine. So it's going to look like this. We'll be down to just one integral left. From 0 to pi. So this part in this we get negative cosine of pi minus cosine of 0. Well, cosine of pi is minus 1. Cosine of 0 is 1. And that whole thing is multiplied by negative 1. So minus 1 is minus 2. And this negative on the outside cancels out the negative. That whole thing ends up just being 2. So we're going to bring that 2 on the outside. So 2 times 2 pi is 4 pi. Here go from 0 to r of r squared dr. Now we got to take the integral of this. So the integral of r squared ends up being 1/3 r cubed from 0 to r. And again, the 0 is going to cancel itself out. And so we get 4 pi over 3 r cubed minus 0 cubed. Well, that's just going to give us where the volume is 4/3 pi r cubed. And that's the equation for the volume of a sphere using calculus with a triple integral. Okay, so we did all that, but you're thinking, well, I could have looked that up in a book. No problem, I didn't have to do all this mess. So let's look at an application where you would actually want to do something like this in order to figure out the volume of a sphere, or maybe just part of a sphere. So here's an application of what we just did, where we don't have to find the entire volume of the sphere, maybe just for a certain range. And so let's say, instead of saying I want the entire radius, I just want this part right here. So let's say this is from 3 to 4 units. So for r, we're going from 3 to 4. And let's say I just want from phi to be from here all the way down to here. And let's say that's going from 0 to 2/3 pi, which is about 120 degrees. So a little bit over 90. So I'm going to go from 0 to 3, or 2/3 pi. And then let's go ahead and swing the whole thing around 2 pi radians. We don't have to. We could have just gone a quarter or a half or whatever. But let's go ahead and do that. And I know I'm out of color coordination, but that's okay. But let's go ahead and do the integral of this, starting off with theta. So these are constants for that. So r squared sine phi, 0 to 3 or 2/3 pi, 3 to 4. Those are all constants as far as theta is concerned. So the integral of d theta is just theta from 0 to 2 pi d phi dr. And so that's going to be 2 pi minus 0, which is just 2 pi. So I'm going to go ahead and bring that out. 2 pi. Here we go from 3 to 4. Here we go from 0 to 2/3 pi r squared sine of phi d phi dr. Now let's go ahead and take care of phi. So r squared is going to be a constant, so I'm going to put that there. That's still the dr, but sine of phi is minus cosine of phi from 0 to 2/3 pi. And so we figure that out. So let's figure that out now. So that's 2 pi. Let's go ahead and keep this integral here. Minus cosine of 2/3 pi minus cosine of 0 dr. Cosine of 0 is 1, so that's minus 1. Cosine of 2/3 pi is negative 0.5. And that whole thing has a negative sign in front of it. So this is negative 1.5 times negative 1, so that's just 1.5. So I want to clean this up. 3 to 4 squared. That's going to be 1.5 dr. And I can move that out. So 2 times 1.5 is 3. So that's 3 pi. And we got to take the integral of this. Well, r squared, we take the integral of it, is going to be r cubed over 3. From 3 to 4. And so if we put these numbers in, let's see what we get. So we get 3 pi, 4 cubed is 64 over 3 minus 3 cubed is 27 over 3. Let's go ahead, and this 3 cancels out these. So we get 64 minus 27 gives us 37. So we get a volume of 37 pi units cubed. And so we're basically just taking this volume here, and we're taking that and spinning the whole thing around over here and getting the area of that kind of a bowl. So if you were an engineer and you're designing this or building this, you would know you need this much material for each one. And so you can make your calculations from there about how much material you need based on how many of these bowls you're going to make. Thank you very much, and tune in again for some more physics and math. Bye.